Hello, and welcome back to the course. We're again looking at Laurent series. So this is section 4.4. We're looking at the second part of this section in the book. So today we're going to actually show that this series exists and how to find the coefficients. So suppose that we have a holomorphic function defined in this annulus. And again, let's not worry about if this really is an annulus, right? If this inside and outside radius are 0 and infinity, we don't really want to call it annulus, but for today, we'll just call all of these annuli just for simplicity. All right, so suppose that we have this holomorphic function, then the Laurent series exists, right? So there exist these numbers Cn, right? Now for n in, of course, all all integers, right? So negative integers, positive integers, right? And we have this double infinite series, right? That's the Laurent series, and it converges to f, uniformly, absolutely on compact subsets of this annulus, right? So just like power series, but now with the negative coefficients added, right? So that's the price we have to pay for the fact that this f is not defined inside, right? This is an annulus like this, so it has a hole over here, right? So for the fact that the function is not defined in its hole, well, we have to pay with these negative coefficients. All right, and these coefficients, these numbers Cn, are given by this formula, which is exactly the formula that we got for power series. It should really be, if there's any justice in the world, right? It should really be just exactly the same. We're doing an integral around a circle of any radius, as long as that circle is inside this annulus, right? And oriented counterclockwise, of course, positively, right? So it looks very much like power series, and actually it should still work if this function f is actually holomorphic inside the larger disk. You will get, so inside the R2 disk, right? So it's holomorphic through the hole. Then you should get the power series, right? Because if this thing is unique, right, then, well, the power series is just the Laurent series with the negative coefficients being 0, right? So this should be equal to the power series then, right? All right, and all the negative guys here would then be 0. All right, so let's prove this. So again, remember, R1 and R2 are the outside radii, right? So let's choose basically a smaller annulus that fits inside our larger annulus. Why? Because we want the boundary to be in an area where we can integrate, because we're going to integrate over the two circles in the boundary of this smaller annulus with radii S1 and S2. We're going to integrate over those circles. So this is the picture, and we define our gamma, our cycle gamma, to be this larger guy, right? And then minus this smaller guy. So we're going, going in the opposite direction on the inner circle. So that's our gamma, right? So now we claim that if Q is in the complement of our big annulus, so it's somewhere here or maybe somewhere here, right? But it's not in this light gray annulus, right? It's not in here, right? Then the winding number of gamma around Q is 0, right? So this is basically we want gamma to be homologous to 0, right? Because we want to use we do want to use the Cauchy formula. All right. How does this follow? Well, if Q is in the hole, if Q is somewhere here, right, then both of these circles go around, right? So if we travel around both of them positively, so counterclockwise, then we'd get 1 as a winding number. And, well, because we're subtracting, we get the overall winding number for gamma is 0. Right, and similarly, if it's outside, if the Q is somewhere here, right, or somewhere here, or somewhere here, right, then neither of these circles winds around. We get the winding number is 0, so 0 minus 0 is still 0. Right? Okay, so gamma is homologous to 0 in this bigger annulus. Right, so now we can apply Cauchy's formula or Cauchy's theorem, right? Now, if we get, so for Cauchy's formula, we're going to apply it to certain z, right? So let z be a point, and it's marked here. Let it be a point in the smaller annulus. So we're going to look at this smaller annulus, only those points, right? Then we have that this gamma winds once around z. Why? I mean, it's the same argument as before. I mean, the outer guy winds once around z, and the inner guy doesn't wind at all around z, right? So 1 minus 0 is 1. All right, so let's apply the Cauchy's formula, right? So f of z for that particular z, right? Or, well, for any z in this annulus, well, that's what it is, right? That's what Cauchy's formula says. Let's split it up into the two integrals. We have the integral over the outer circle, and we have the integral over the inner circle. And what I'm going to do, if I write it as the integral over the inner circle, which normally we say, we sort of the default orientation is the positive one, I put a minus sign in between, right? So that's this minus sign over here, right? And we will expand these two integrals separately. We're going to find a series for this guy and a series for this guy, right? And this guy is going to be the positive terms. This guy is going to be the negative terms. All right. So if we have, let's look at the first term, right? The big circle. So if zeta is in the big circle, right? Z is in, it's in our smaller annulus, in between S1 and S2. So in particular, if zeta is in the circle, then, the distance between zeta and P is exactly S2, right? That's the point of it being a circle, right? And Z minus P, right? The distance between Z and P is less than S2, right? Because we're inside the annulus, so we're inside the bigger circle, right? So that means that this guy is strictly less than 1. So we're going to use this in a geometric series, right? So we're using basically the same idea as we did for power series, right? And actually for this bigger circle, it's essentially exactly the same, right? So we look at the integral, right? And now we look at the Cauchy kernel, 1 over zeta minus z. And we want to sort of move the z into its own sort of geometric series, right? So we rewrite the Cauchy kernel as this, right? So we replace the zeta minus z with zeta minus p. We have to pay for that, right? So we, this guy is really zeta minus p divided by zeta minus z, right? To make it work out, and you rewrite that with a little bit of algebra like this. So now it looks like a power series, right? And geometric series, and we have precisely this estimate. So we know that this actually converges really nicely. So, all right. So let's replace this guy with the geometric series, right? The convergence is nice and uniform as the zeta moves along this circle, right? So it's uniform for those zeta, right? Because this estimate, right, it didn't depend on zeta whatsoever, right? So again, we have we can switch these, switch the integral and the sum, right? Because of this uniformity, right? And now we have, this is not quite exactly the formula that we wanted, but it's almost the right formula for the Cn, right? But the main thing is that if we make this the Cn, then we see that the first term in that in the sum of these two integrals is precisely a series, right? Now just going from n equals 0 to infinity. So these are the coefficients, and I have z minus p to the n, right? So it's the right sort of series, and it just has the zeroth and the positive coefficients, right? So it is the right thing, right? And again, the series and the integral swaps because of uniform convergence. You always, whenever you swap limits like this, you always have to have an argument why that works, right? Works by uniformity here. It is the convergence of the geometric series or power series in general is very nice, right? That's the whole point. All right. So now let's look at the inner circle, right? So let zeta now be on the inner circle, right? So now we look at, now we want to look at this guy, right? So z, the distance between z and p is bigger than S1. So that's why I'm looking at this term, right? So I have S1 divided by z minus p absolute value. That's always less than 1. That's the geometric series that I want. And turns out I can't do that. I will need this minus sign, right? So if I take minus this integral, right? So that's the thing that I'm going to be adding to the previous thing, right? And I take a look at the Cauchy kernel. I again rewrite it like this, where I have this, this term that looks like something I can expand with geometric series, and it's this term over here is precisely the right thing, right? It's precisely the thing that's uniformly strictly less than 1, right? So I again get, I get the series over here, right? I can swap the series because of the uniform convergence. And so here, if you notice, I used m for the index, right? So when I swap and when I leave the z minus p inside, I take the z minus p outside and I leave the z minus p to the m inside. Well, I really want to get it should be 1 over zeta minus p to the n plus 1. Now, of course, n is going to be negative, right? M is positive, right? But this is the thing that I want n to be, right? So if I relabel my series so that n is minus m minus 1, I get this, right? So I have to then go from minus infinity to minus 1, and I get precisely the z minus p to the n, the right thing. And over here, again, I get the right formula under the integral. And that's going to again be my Cn, right? So now we have the second part of that integral is now again this Laurent series now, right? Now we do have actual negative terms, and we only have negative terms, right? So when we add those two together, right, we got positive terms and the negative terms, well, also the zero term, right? So they don't clash, right? I mean, I only computed the positive terms before, and now I've only computed the negative terms. All right. So we have the series, right? But we didn't quite get the formula for Cn for any radius S. I mean, we got it for for the positive ones we used S2. For the negative ones we used S1, right? So let S be anything whatsoever. in between R1 and R2, any number, right? So let's look at a circle of radius S. Now, if we, if we look at this cycle, again, just like before, this is homologous to 0, right? I'm adding a circle and subtracting a circle, right? And so that's going to be, again, homologous to 0, right? And if we look at this function over here, you notice that it is holomorphic on the entire annulus, right? And so if I just apply Cauchy's theorem, I get that the integral of that function with respect to this cycle over here is 0, right? Well, that's precisely the difference between these two integrals, right? So I might as well have integrated over the S circle. I get the same number as if I integrated over the S1 circle, right? And similarly for S2, right? So we get that this is true for all Cn, right? So we can integrate over any radius S and get the same numbers Cn. Okay, convergence. So for any epsilon, every small epsilon, we get that because the geometric series used in the first part, right, for the positive ends, that converges uniformly, absolutely, basically, in this smaller, compact disk, right? So that means that I have, uniform absolute convergence on compact subsets of delta S2, right? Of that part of the series, right? Not the whole series, because compact subsets over here could include the whole, right? But they cannot include the outside, right? On the other hand, the second part of the series, so now this is basically the disk sort of flipped across, right? But we will get that part, that series converged uniformly, absolutely, when this thing was less than or equal to 1 minus epsilon. So it actually works on it converges uniformly, absolutely on compact subsets of the complement of the closure of the inside disk, right? Now, again, those could be, many more compact subsets that include lots of the outside, just nothing from the whole, right? But if we have any compact subset of the larger annulus that we're looking at, right? Then, well, that compact subset is going to be compact in delta S2 around P for some S2, and it's going to be compact in here, right, for some S1, right? And so then we compute the CNs for that S1, S2. That's the same thing as computing them for any S, right? We get that series converges uniformly, absolutely on compact subsets, right? On that compact subset, right? And it's the same series that we got, right? All right, so now we get the right convergence. That series that we get with those coefficients that we computed with circle, any circle whatsoever, right? As long as it was inside the annulus, that series, that Laurent series, converges to our function, right? However, that doesn't mean. Oh yeah, so that's I said that, but now I have it on the slide. So that doesn't mean, of course, that we have uniqueness, right? That series, where the coefficients are computed in that precise way, that converges, and they're sort of unique up to changing the circle, but we don't know if there's maybe a completely different way of computing these coefficients that maybe gives you a completely different Laurent series that also converges to your function. Maybe that's possible, right? So let's show that it isn't. And here it's a little bit more complicated than for power series, where you can do this by differentiating. Here we cannot differentiate at the origin because the function isn't defined near the origin, right? So we'll do a different trick that still works for power series. It's that idea is still there as well, right? So suppose that we have another Laurent series that also converges uniformly absolutely on compact subsets of this annulus, right? Let's show that the dn's equal to cn's, right? So, well, let's compute the cm. We have a formula for the cm, right? The formula for the cn is this for some s, right? Okay, now we have that f is actually equal to that, right? We're saying it's also equal to this series, right? So we'll plug that in. We'll plug that in to here, right? We plug in the series. Now it converges uniformly, absolutely on compact subset. That's a compact subset. So we can swap. We can swap the integral and the series. And so the integral goes inside, and we look at this, this expression over here, and then we notice that most of the time this is 0, right? You can except in one case this is 0, right? Except when the coefficient, the exponent here is -1. Except in that very particular case, this is always 0, right? This is just the integral over power over a circle, right? And the only power where you get into trouble is the negative first power. Well, you don't get into trouble; you just get non-zero, right? So that's when you get the 2 pi I, and you get that the whole thing equals dm, right? And this is the the reasoning. It's only when n is equal to m that you get anything, and you get precisely the right thing. So it's the only dn here that survives, right? Is the mth one. So we get that cm is equal to dm. Therefore, the series is unique. All right. So we've proved the existence and uniqueness of the Laurent series, and we have a formula for the coefficients too. All right, now let's talk about how we can differentiate and anti-differentiate. This term is going to be exercise. It's the same idea as for power series. I guess there's one more sort of hitch here. We cannot anti-differentiate the negative first exponent. So the negative first term in the Laurent series, that does not have an antiderivative, right? So we can't anti-differentiate it. So this is the proposition, right? So if we have a function and it's given by this Laurent series, converging uniformly, absolutely on compact subsets of this annulus, then f is holomorphic, it's complex differentiable, and its derivative is defined by this this series, and that converges on the compact subset of the annulus, right? So we can differentiate formally, right? We just differentiate term by term, just like for power series. And moreover, as long as this term is not there, right, then we can anti-differentiate. There is an antiderivative, and it has this formula. Again, we're basically doing this formally, so we can formally anti-differentiate, of course, except for this term, this minus first term, right? Okay, and this is an exercise. Right, a couple more useful exercises. So one that is relatively very easy is if I take some holomorphic functions and I take a linear combination, then you do the same thing to the Laurent series coefficients, right? That's how you compute the Laurent series coefficients for the linear combination of these functions. And another useful exercise that's maybe more useful exercise for the last lecture really is how do you find these Laurent series? You don't do it by computing those integrals, right? Just like last time, you really do it just by computing in some sort of ad hoc way. Generally, rewriting. If you have some rational guy like here, what you do is you try to rewrite so that you introduce the right geometric series. And so try to do this in the annulus around 0. Actually, it's just that's going to just be a power series, right? Because you get that this f is actually holomorphic at 0, right? So it's actually, you're just going to find the power series. Then try to do it in this annulus around 0, where the radii are between 1 and 2, right? And then try to do it in this annulus, where the radii are between 2 and infinity. This f is holomorphic in all three, and you can find the Laurent series expansion for this, right? Just by doing algebra, just by basically massaging it into the right geometric series. All right, so that's it for today. So next time we're gonna look at we're actually gonna start looking at chapter 5. We're gonna look at zeros of analytic functions, the zeros of holomorphic functions. And we're skipping the rest of chapter 4, which is sort of optional, still interesting stuff. But we're gonna skip the homotopy versions of all of these because it's more. We want to get further, right? So you'll of course welcome to read it in the book. But we're gonna skip to chapter 5 next time. All right. So see you next time.